Hello everyone, I hope you're all doing well. We're going to be solving a very nice short problem on moments about a point using the scalar approach. Okay, so here is the problem. And we'll go over this problem step by step when we make use of the right hand rule to compute the resultant moment. Okay, so in this problem I have a long thin beam. So I'm going to draw that long thin beam here. Okay. And on this long thin beam, I'm going to have a couple of forces acting. Okay, the first force is acting in the following manner. Okay, it's acting at an angle of 30 degrees to the vertical. So here is the actual force. Okay, and this angle, which I'm going to draw in a minute, this is a force of magnitude 30 newtons. And it is at an angle of 30 degrees from the horizontal. Okay, and this is acting at the point A of this beam. Then I have another force that is acting at the point B of this beam, and that force is shown here. Okay, so this is the point B where that force is acting. Here is the point A. This force is a magnitude which I'm going to call as F2 of 50 newtons, and then I'm given a triangle here, which is your typical slope triangle. Whenever you see a triangle given in statics with some numbers on it, that is a slope triangle, that is a right angle triangle. Whether it looks like one or not to you, in our class at least, that's going to be a right angle triangle. Okay, all right. Now this beam is pinned about a certain point, which I'm going to label here. Okay, so this is pinned somewhere here. It's not necessarily in equilibrium. I'm not too worried about it yet, and neither should you be right now. And I'm given some distances from the point where it is pinned, which I'm going to call as the point O. Okay, so this is the point O. Right from point O to point A is 1 meter in length. Okay, so I'm going to mark these distances with dotted lines, as you will see in a minute. Okay, from here to there is 1 meter, and from point A to point B is also an equal distance of 1 meter. Okay, so these are going to be dotted lines. Likewise, all of these as well here. I just came to know about this very nice feature on Notability where I can draw dotted lines, so I'm just showing off to you now. Okay, all right. So here is the distance from these 2 points. So this is 1 meter, this is 1 meter. Okay, the beam does not have any thickness that is given to us, so its length is much longer than its thickness, so we're not too worried about the thickness of the beam. Okay, we can neglect the thickness of the beam. Okay, so we neglect the thickness of the beam. Okay, you're told that the point O is the point of interest. So point of interest is the point O. Okay, and then the points of application of the force. These are the points A and the points B. Okay, and what am I supposed to find in this problem? I'm supposed to find the resultant moment about the point of interest. Okay, obtain the resultant moment about point O. And that's why I know that the point O is the point of interest, because they're telling me, that hey, there is something going on. Find out what the effect of this force is on the rigid body, which is the beam, about the point O. First thing that you got to notice here is that there are no axes given to us. So I'm going to draw my axis system. Okay, I'm just going to draw an x, y, and a z direction. So I'm going to call the vertical axis as the y-axis, according to the right hand rule. Okay, I'm going to call the horizontal direction here, which you can see as the x-axis. Okay, and then I'm going to have an axis which is coming out of the page here, which is going to be the z-axis. Okay, so these axes were not given to me. I'm drawing them myself. And then the second thing I realize is that this is a two-dimensional problem. Okay, the forces are acting on the xy plane. The distances are on the xy plane. Okay, so that's something that I'm going to realize. Okay, so from the problem, so see from the problem given, okay, these are the steps that I'm taking to solve the problem. Okay, first step is I set up my axis system, set up an axis system. Then we realize that the problem is 2D. Problem is a planar problem, or 2D. Okay, and then realize that the forces are on the XY plane. As you can see, if I scoot up, the forces are on the XY plane, which is quite obvious to us. The distances are also on the XY plane. The distances are also marked on the XY plane. And since the direction of the moment vector is perpendicular to the plane containing the force and the distance, the moment is obviously going to be along the Z direction. Okay, this tells me. So we find out. Since moment vector is perpendicular to the plane containing the force and the distance, this implies that the moment vector for this problem should be directed along the z-axis. Could be positive or negative. Positive or negative, we don't know yet. Okay, this one we do not know yet because we haven't started solving the problem. So a couple of key words that I want to underline. Moment vector is perpendicular to the plane containing the force and the distance. Okay, the forces are on the XY plane. The distance in this problem are also marked on the XY plane, which means that the moment vector has to be perpendicular to the plane containing the force and the distance. So the moment should be directed along the z-axis. Okay, so in this case, the moment vector in this particular problem, okay, for this problem, should be directed along the z-axis. Okay, I hope that is clear. And so I have all this setup done. So here is what I'm going to do. I'm going to take this figure and bring it down so that I can start working my details on this. Okay, so I'm going to take all of this with the axes present. I'm going to copy that and I'm going to bring it here. All right, fantastic. What am I going to do? Well, let me first arrange it nicely. All right, this is better. So what am I going to do? The first step I will do in any problem I see is, okay, hey, I want to take these forces and I want to break them into their components, okay, because they are at an angle. So let me do that. Okay, so let me take this guy and bring it on here. This is the point of interest, which is the point B. I guess that doesn't let me select it. That's okay. So I'm going to take this force and break it up into its components, starting from the point of application. Please always notice my components always start from the point of application. Okay, the point of application of this force is the point B, which means that my components are going to be starting from there. My components are going to be starting from there in the horizontal and the vertical directions. Okay, and let me extend this a little more. Okay, let me take this creature and move him here, which I know is the x-axis, and then the forces. What are the forces? If the magnitude of the main force is 50 newtons and the triangle is a 3, 4, 5 triangle, then this is going to be 50 times 4/5 and 50 times 3/5. Okay, so this is going to be a force that is 50 times, using the idea of similar triangles. Okay, this is 50 times 3/5 Newton, and then this force is going to be 50 times 4/5 Newton. Okay, that's the important thing in this particular problem. Okay, or if you want to call them as F1 and F2, you can call them as F1 times 3/5 and F2 F2 times 3/5 and F2 times 4/5. Likewise, I'm going to take this force here and break it up into its components as well. Okay, as you can see, this is the point of application, which is the point A, so my components should be meeting at that particular point. Okay, so these are my components for this particular force. Okay, there is one component here vertical, there is another component here. This is F1, which is sine F1 is 30 newtons, so this is going to be F1 times sine 30, and then this creature is going to be F1 times cosine 30. And just to be uniform, let me also write this as F2 times all these values and so on. Okay, so this is going to be F2 times 3/5 and F2 times 4/5. All right, this is very beautiful. What am I going to do next? The next thing I realize is this. Okay, hey, if you look at that F1 cosine 30 force, right? If I take its line of action, which is this line here, and if I extend its line of action, you see that this line of action is going to intersect the point O. Likewise, I take the line of action of the horizontal force F2 times 4/5 Newton. That is also going to intersect the point O, which means these will not be of any use to me in my problem at all. Okay, so this is what I'm going to note down. Okay, so if I extend the line of action of the forces F1 cosine 30, so many newtons, and F2 times 4/5 so many newtons, we see that they will intersect the point of interest. Okay, which obviously tells me that, okay, hey, these forces are not going to cause any moments. Okay, so which means that these forces will not cause any moments about the point O. So keywords once again here, if you have the line of action of some of these forces intersecting the point of interest, then these forces will not cause any moments about that point. Okay, which means that from the point of view of the forces that are useful to me, right? So this F1 cosine 30 is of no use to me. This F2 times 4/5 Newton is of no use to me. Okay, which means the only useful forces are F1 sine 30 and F2 times 3/5 newtons. Okay, so I'm going to once again redraw my figure so that I can use some of this information. So I'm going to copy this beam here. Okay, I'm going to copy this beam and then bring it down here. So this is now going to be my only useful set of forces. Okay, I have my axes, which will be drawn once again. Okay, this is my y-axis, this is my point of interest, which is the point O. Okay, then I have my x-axis, which was directed all along the length of this beam, so this is x-axis, and then I have the z-axis, okay, which is directed out of the plane of the paper. And then I had my forces. The only forces which are now of interest to me are F1 sine 30, okay, which is acting here. I'm planning to draw a vertical line. Sometimes these creatures are abominable. Then I have this force here, which is the 3/5 Newton. Okay, so this is essentially going to be the following. Okay, so for me this force is going to be F1 times sine 30, which is 15 newtons, and then this is going to be F2 times 3/5, which is going to be 30 newtons. Okay, where F1 and F2, we knew the magnitudes of these 30 and 50 newtons. Okay, so this is all I'm doing, the simplification. Then I have the distances which I can mark very easily from the point of interest to the point of application of these forces. Okay, likewise from here to there. And I have this long guy here. I'm going to draw it as dotted lines, as you know by now. Okay, so this is going to be a dotted line, then this is going to be a dotted line, and lastly this creature here. Okay, and then I'm going to have my arrows. Okay, this is a distance of 1 meter, this is a distance of 1 meter. Here is the point of application of that force, which is the point A. Here is the point of application of this force, which is the point B, and all I have to do is use the right hand rule and make up with the fundamental idea that the resultant moment about the point O. Okay, so the key idea now, the resultant moment, which I'm going to call as MOR, about the point O, is the moment about O due to the force F1 plus the moment about O due to the force F2. Okay, I'm going to do a few more details. Okay, and I'll sneak in and add the other two forces that we kind of ignored because their distances are 0. And so if I look at the force F1, right, I see that the force is in the vertical direction. The distance, perpendicular distance from the line of action of this force, okay, so all the way from here to there, I extend a line parallel to that force, and I see that, okay, the perpendicular distance is going to be this much, which is 1 meter. Okay, which means the magnitude of this moment, okay, so MOR is going to be from the force F1, it's going to be F1 sine 30, okay, times the perpendicular distance of 1 meter. And then if you use the right hand rule, align the fingers of your right hand with the direction of the force. Your palm faces the point of interest. Curl your fingers. The direction of your thumb is out of the page. So the direction of the moment due to this force is in the Z direction. Okay, so this is going to be in the Z direction, and I'm going to mark it here based on a person who is sitting here and observing these forces. The moment due to the force F1 sine 30 is going to be directed counterclockwise about the Z-axis. So this is going to be F1 sine 30 times 1. Okay, likewise I had the other force which belonged to this, which was this F1 cosine 30, and I will say that its distance is 0, right? The perpendicular distance, as we have said, its line of action intersects the point of interest, which means its perpendicular distance is 0. Okay, and then I go to the next set of forces. This is the moment due to the force F1. Then I go to the moment due to the force F2. I go back to my figure here. Once again, the force is vertical, the distance is horizontal. What is the perpendicular distance? Here is how you calculate the perpendicular distance. Draw a line parallel to the force F2. Okay, I'm going to extend the line of action of this force here with your permission. And then all the way from the line that you have drawn to this line of action, which has been extended, is going to be 2 meters, and that is the perpendicular distance. Okay, and then the moment is going to be F2 times 3/5 times the distance of 2 meters. And then what is the direction? Be careful here. Right hand rule. You're going to see some pain in your palm because you're going to be twisting your hand. Take the fingers of your right hand, align it to the force F2 3/5. Your palm should be facing the point of interest. Curl your fingers. The direction of the moment is going to be into the page because the direction of your thumb is going to be into the page. Okay, so if I do that according to the person who's sitting here and observing the moments, this is going to be F2 times 3/5 times 2. Okay, that is the direction of that moment, which means that it's going to be a negative k. Okay, so this is actually going to be minus k. And you're going to have the other one, which is F2 times 4/5 times 0 in the k. That doesn't make a difference whether it is positive or negative k. Okay, so here this is gone, we just got rid of them. And then if I do the resultant moment here, all I have to do is add up these two. This is going to be f1 sine 30, which we already written as 15. So this is 15k. And then this is going to be f2 times 3/5 was 30. So 30 times 2k. Okay, which means that the resultant is going to be the algebraic sum of these two. It's going to be minus 45k. Important is the units, Newton meters. Okay, so which tells me that the resultant of these two is a moment that is directed along the negative z-axis. Okay, so this tells me that the resultant moment is directed along the negative z-axis, and its sense is viewed as a clockwise rotation by a person sitting on the positive z-axis. Okay, so essentially what this problem is trying to tell me, okay, that the resultant moment due to these forces is going to be clockwise, or the entire body is going to be rotated. So the net effect of these forces is to try to rotate the entire body clockwise. Okay, so which essentially tells me that the net effect of the forces on the beam or the body is to try and rotate the body in a clockwise sense. Okay, this is the net effect. All right, so this is the problem, and a fairly straightforward problem if you get used to this idea of the right hand rule. Okay, that is the most important thing. Please get used to the idea of the right hand rule. Okay, the right hand rule is the most important thing for you at this point in time. Okay, so please get used to the right hand rule for moments. Okay, what is the right hand rule? We have gone over this in my online lecture on moments about a point using the scalar approach, but very quickly, take the fingers of your right hand, choose one of these forces. I'm going to choose the force F1 sine 30. Take the fingers of your right hand, align it with the direction of the force. Okay, then your palm should be facing the point of interest, which is the point O. Once you're done doing that, curl your fingers. The direction of your thumb, which is going to be pointing out of the page in this instance, is going to be the direction of the moment, which is marked as a double arrow, which is coming along the positive z-axis. And this is viewed as a counterclockwise rotation by a person who is sitting on the positive z-axis. Okay? And likewise, if I do the same thing for that other force, F2 times 3/5, if you use the right hand rule, face your palm at the point of interest, your fingers aligned with the force, curl your fingers, your thumb is going to be pointed into the page, which means that it's going to be viewed as a clockwise rotation by the person who is viewing these events. All right, please practice these problems. You'll have many more practice problems I'll upload, and I think we should be good to go on this. All right, thank you very much. Bye-bye.